hey everybody, welcome to Tuesday. Just a quick little thing right off the bat. What I'm going to do today is kind of give you a lot of stuff, but I'm going to kind of be like, hey, this is for Tuesday and Wednesday. So you can kind of split it up however you want. There will be a pretty natural kind of breaking point, but I just kind of want to give you stuff and then have you decide on your own time when you want to do it. Just because the daily thing, I know it's kind of tedious and it's kind of tricky. So I'll try to kind of switch to that more so just because it's a little bit easier for you guys, a little bit easier for me. Yeah, so just kind of that note. But so what we're doing today is we are kind of revisiting this model that we started to build yesterday. I read a lot of your answers and I was like, yeah, we remember a lot of thermodynamics, which is good and exciting, especially because thermodynamics has a lot of weird definitions to it. And there's a lot of weird terms that we use colloquially that we have to make sure that we're using in a specific way when we're doing thermodynamics, like temperature or heat. All these terms we use every day, not every day, but some days. We use them in our everyday life, but it may not be the same definition that we use when we're doing actual physics. So what we're going to do today is I'm going to kind of do a little review lecture with a few practice problems built in towards the end. So you're going to have two Google Forms, one with the practice questions, and then one with kind of a longer free response style AP question. I think we have already done this question, but it's good to revisit it and good to look at one of the type of questions we may see on the AP test. So yeah. So what we started off with yesterday, what we kind of did yesterday is answer some questions about good old tea. So the first thing, one of the first things I asked you was, why does it take less time for the hot tea to steep compared to the cold brew tea? And we said explain this based on what's actually different about the particles. And what we're going to do and kind of keep on building up and going back to help us think about thermodynamics is this particle level model. So we really want to be able to build this particle level model to explain and help our understanding about what we see going on. So I don't know if yeah, so this was somebody's answer, which I really liked. So somebody said, in a hot liquid, the particles are moving much more quickly, so there are more collisions between the water and the tea bag for a hot liquid. So the tea and the water would be mixed more quickly. In the cold liquid, the particles are moving more slowly, so it takes much longer for the water and tea to mix, since there aren't as many collisions. So we have this idea and we have this model that we can think of particles as tiny little objects, and really the temperature is controlling the speed that these things are moving at. And the person who answered that, they correctly identified this idea that the steeping of the tea, the kind of bringing out of its flavors, is happening from these collisions. These collisions are kind of knocking the flavor out of the tea bag and into the water. That's a very rudimentary understanding on my part, saying that's knocking the flavor out, but it gets the job done and it's a helpful model. But so we're really thinking about what's happening with the individual particles. This person is referencing these particles are moving quickly, not just, oh, the thing was hot, so it did stuff. We're thinking about what are the particles physically doing and how is this working? So moving on to the next question, now that we kind of have this idea of particles in mind and this idea that we want to work from a particle model, is this question where we're saying, okay, the boiling water was at a temperature of 100 degrees Celsius. What does temperature measure? What does temperature actually mean when we talk about it in a physics sense? So when we talk about temperature, the person who, or sorry, this was another question. So somebody answered, they said how fast the particles are moving. That's what they said for temperature. And that's a really good start. That's a good place to think about and a good place to be like, okay, yeah, the temperature is controlling the speed of the particles. When we think about temperature, the main thing that we want to think about, where our minds want to go to, is that the temperature is telling us the average kinetic energy of the particles, which is absolutely related to how fast the particles are moving. So we want to think about the temperature as the average kinetic energy of the particles. And when we talked about kinetic energy, or when we talked about the temperature, we said that we have this equation that helps us relate the average kinetic energy of an ideal gas to the temperature of that ideal gas. So we have this equation that says our kinetic energy is equal to 3/2 times kb, which is a constant. It's a Boltzmann's constant. It just kind of helps our units work out, times the temperature. So we have this cool idea that the kinetic energy is directly related to the temperature of the gas. So if we look at the gas and we say, okay, it's at some certain temperature, the kinetic energy is directly related to that. So that's a kind of nice statistical way of looking at energy and its relation to temperature, and kind of revisiting this idea where somebody said, oh, it's based on how fast the particles are moving. So yes, but let's extend that a little bit further. So we know down here, based on our study of energy before, that the kinetic energy of an object is equal to 1/2 mv squared. And we can think about a gas or a fluid or really anything as a bunch of tiny little particles moving around. And we can think about each one of these little particles has some amount of kinetic energy to it. So if we're kind of revisiting this, we can say, okay, well, we can say that kinetic energy is directly related to this temperature, right? If I kind of were to graph this, I'd have a slope of 3/2 times the Boltzmann's constant, and they would be directly related to each other. If I increase kinetic energy, I would increase the temperature by the same amount. And then if we kind of extend that further, if we set this kinetic energy, this 1/2 mv squared, equal to this 3/2 kb times t, we see that the temperature here is directly related to the square of the velocity. So if we kind of just look at this really quick, a quick little simulation to help us think about energy and particles. This isn't the best I mean, it's a good simulation, but it's just kind of hard to visualize, I think, but it helps a little bit. But we can think about, here we have these particles in here. I'll just kind of pump some in there. Right now it's at 300 Kelvin. So then if we start to increase it, we add heat, we are increasing the temperature, and we see on average the kinetic energy of our particles is increasing. We can see, okay, well, that temperature went up. As a whole, these particles got faster, and they're not all moving the same speed, which is a big idea that we're going to talk about. But on average, the speed, this curve of what we're looking at, has increased. And we can see up here, it's kind of telling us the root mean square, the average speed of all these particles. It increased and went up. So if we started off again, let's see the two pumps. They started off at about 500 meters per second. I increase the temperature. Let's see, let me double the temperature. Or maybe I'll quadruple it. I'll go up to 1200. I missed it a little bit. But so, yeah, increase the temperature and the speed goes up. And what we want to be able to talk about a little bit is, hey, if we increase the speed, if we increase the temperature, how does the speed change? That's going to be one of the things that we're going to be able to focus on. And we're going to be able to do that by looking at the relationships between these variables. So yeah, one thing we want to talk about is if we double the speed of these particles, we're really quadrupling the temperature because of this relationship that we've established. This 1/2 mv squared is directly related to this 3/2 kBt. These kinetic energies, we can set them equally to each other. So because we have this squared term in our velocity, if we double that velocity, if we double the speed of our particles, we're quadrupling the temperature. So if we quadruple the temperature, we are doubling the speed. So that's just kind of a cool way where we can look and see, hey, like, what are these particles doing? And when we actually increase the temperature, what is happening to the velocity of those particles? So just a couple quick little example questions, some quick little ones just to kind of talk about and go over. So right here we have two objects. We have this object A and we have this object B. And we're saying, okay, object A is at 200 kelvins and object B is at 800 kelvins. So which one of these has a greater kinetic energy? So think about that for a quick second. And we'll talk about it. Here's a quick second. So yeah, with this, we should be able to pretty quickly identify, hey, the temperature is directly related to the kinetic energy. So if we have a greater temperature, then we have a greater kinetic energy of those individual particles. So we can see that object B is going to have a greater kinetic energy because it has a greater temperature. So that kinetic energy is a measurement of the average kinetic energy of all of our particles. So because we have a greater temperature, we have a greater average kinetic energy of those particles. And now we're looking at this little question. So this one gets a little bit more complicated. If we ask, what is the ratio of the velocity of the particles in B to the velocity of the particles in A? So how could we set this up? How could we do this? Again, take a quick little second. We don't have to go too much time. But just take a quick little second and try this out. See what this relationship is. See what you find for this ratio. If we have quadrupled the temperature, how do our speeds have to change in relationship to that? Let's give that a quick think. And then here we'll just kind of talk about it. So what we can do if we want to set this up and kind of figure it out mathematically and kind of plug in numbers and use equations, what we can say is that the temperature of B, this object B, is 4 times the temperature of A. So this one is 200 kelvins, whereas the other one is 800 kelvins. And what's nice is we're using this absolute scale of kelvins. If we're using something like Celsius, then quadrupling that temperature isn't necessarily 4 times it, which is kind of weird because we don't start at 0. It's not an absolute scale. But because we're using kelvins, we have this absolute scale. We start from 0 and can only go up from there. So if we're looking at this temperature of B is 4 times that of temperature A. 4 times 2 is 8. So we have 800 kelvins for temperature B. And then what we can do is kind of say, oh, how are these all things related? Well, we want to end up with is a ratio. So we know that really everything's going to have the same mass. We're going to assume they're made out of the same material. They have the same Boltzmann constant because that's constant. 1/2 is going to be the same. 3/2 is going to be the same. So what we can say is the temperature of A is directly related to the kinetic energy of A. So then if we kind of extend that a little bit further and plug this equation in, so they kind of relate them through the kinetic energy, then we can say that the temperature then is directly related to this velocity of A squared. So we say, hey, this is directly related to that. So in this case, directly related to V squared. And then we can set this up for B, for our object B. But instead of plugging in TB, let's plug in our equation for TB, this 4 times TA. So you can say 4 times TA is directly related to the kinetic energy of B. 4 times TA then is directly related to VB squared. And then we can kind of set up a ratio. We have something that's directly related to VB squared, something directly related to VA squared, and we can set up the ratio. So we can do VB squared over VA squared is equal to what we found, so 4TA over TA. We can divide out a TA because it's a ratio. We have TA on the top, TA on the bottom. So we get VB squared over VA squared is equal to 4 over 1. And then take that square root to simplify that out. And we get that VB over VA is equal to 2. So the particles in B are moving 2 times with 2 times the kinetic energy, or sorry, 2 times the velocity as they are in A. Sorry, I heard like a weird noise. I didn't know what that was. Yeah, so the velocity of particles in B are moving 2 times as quickly as the ones in A. So it's double the speed for quadrupling the temperature. And then one other quick little question about this idea to kind of think about and pause it. But so we have one block is at, if we're looking at situation A and B, let's say we're kind of heating one of the sides, so it kind of increases the temperature of one side and not the other side. If we're looking at this example, let's say A has one side that's at 200 kelvins and then another side that's at 250 kelvins, and then B has one side that's at 800 kelvins and the other side's at 850 kelvins. So which process shows a greater change in thermal energy between these two? So take a quick second, think about it. All right, so this kinetic energy is really the energy in our system, and thermal energy is going to be made up of the kinetic energy of all these particles. So we see, because we're dealing with this Kelvin scale, a difference of 50 kelvins is the same regardless of if we're in A or B. 50 kelvins is just going to be 50 kelvins, which means that they have the same difference in temperature, which means they have the same difference in kinetic energy, which means they have the same difference in thermal energy, because thermal energy is really just, hey, what's the kinetic energy of all these particles? All right, so they're going to be the same because energy is directly related to the temperature. All right, and then if we're kind of thinking back about another question that I asked you all, so we said over time the tea in my cup sat out and got cooler. What is exactly happening when something gets cooler? Explain. So what we can say is we're kind of building up this idea of these particles, they have energy, there's this idea of thermal energy. So what we can say is that there was an exchange of energy. And what we're going to call this process of exchanging this thermal energy, we're going to call this heat. So this process of exchanging thermal energy, we're going to call it heat. So this picture is kind of to the side, so it doesn't super represent everything that's going on, especially because when we have a cup of tea, it's not a closed system. We still have this air is moving all over the place. But what we can say, and what a lot of you all said when you answered this question, is in the liquid, in the tea, I don't want to like show it to you, but I don't know. It's tea, you can take my word for it. got tea in the cup. But so inside the cup, we have particles that are moving quickly. They're at a high temperature, which means that they have a higher kinetic energy. So these particles are all moving quickly. And what we know about particles is that they can collide with one another. So we can think about it as a bunch of little balls. Like if you were playing a game that had a bunch of balls together and they were all moving around quickly, they would collide with each other. So the same thing is happening with our particles. So this was heated to 100 degrees Celsius. And the air in the room is not. It's about room temperature, so it's about 25 degrees Celsius. So the air is a lot cooler. These particles are moving slower. In the tea, the particles are moving a lot quicker. So they're interacting with the particles in the air. They're transferring their kinetic energy when we have this collision to the lower temperature particles, and they're heating them up, or they're giving them some of the energy, and they're able to speed up. So the temperature of the particles, the surrounding particles, is increasing. Their speed's increasing due to those collisions, and they're getting this increase in temperature, this increase in kinetic energy. So if we're looking at this idea of heat, we're really saying that heat is the main method for why this is happening. Heat is the explanation. Heat is really what's telling us what's going on. So if we're going to define heat, which is going to be important because it's one of those words, again, that we use colloquially, but the physics definition is very technical. So when we're talking about heat, we're saying when energy is transferred because of a temperature difference, that energy is called heat. So if we're thinking about heat, heat is the transfer of thermal energy because of a temperature difference. So one of the main ideas when we're thinking about heat is a process. Objects don't have heat. I can't say, oh, this tea has heat, and say, oh, this heat has thermal energy. I can say this heat has a high temperature. I can say this tea has a high kinetic energy, but I can't say that it has heat. Heat is really a process. Heat is telling me, oh, I'm transferring thermal energy. I'm having these particles collide, and that's causing some sort of exchange of energy. So heat is a process. It's not a thing, it's a process. And yeah, so here we see this process of heat transfer. We see that this thermal energy is exchanged between my high temperature particles and my low temperature particles until I reach this thermal equilibrium. So heat is a process. And then when we're thinking about this process, if we think about, oh, when will it stop? So heat will flow from higher temperature to lower temperature objects until they reach thermal equilibrium. So until the particles have the same average kinetic energy, until it's no longer energetically beneficial or probable for an exchange of energy to occur as a whole. So yes, some of these particles, this is kind of an ideal situation where we're saying, oh, they're all moving the same speed. So on average, yes, they have the same speed, but eventually they'll kind of give each other energy and they all kind of level out to some average velocity, and then by default an average kinetic energy. But so eventually we'll have, maybe at first we have all these really fast moving particles colliding with really slow moving particles, but eventually when the fast ones collide with the slower ones, the faster ones will lose some of this energy, the slower ones will gain some of this energy, and this keeps on happening until eventually they've all kind of settled out to have, on average, this same velocity. So it will eventually end when we reach this thermal equilibrium, where everything has the same kinetic energy and everything on average is moving at the same speed, or with the same kinetic energy. Because yeah, then we have the mass, and sometimes the mass gets in the way. But so when everything has the same average kinetic energy. And then just to kind of take a quick break, look at some definitions. So just because I've been using these terms, I want to make sure that we're using them correctly. So thermal energy is the sum of the microscopic kinetic energies and potential energies of all of the molecules in an object. I just kind of wrote in kinetic energies because we're not going to think too much about potential energy. Our equation way back here dealt with kinetic energy. So we're really looking at the microscopic kinetic energy of all the molecules in an object. So that's our thermal energy. So we can pretty much think about thermal energy and this kinetic energy of our particles as the same thing. We don't talk about macroscopic kinetic energy as thermal energy. So if an object is just moving with some velocity, my calculator doesn't have thermal energy because it has a kinetic energy. It has a thermal energy because of the kinetic energy of all the little particles that are making up this calculator. So we just said that heat is energy transferred between two objects because of a temperature difference between them. And then temperature is the measure of average energy of the atoms that make up the object. So either the average kinetic energy of them or the average thermal energy of them. We're going to talk about them kind of in the same way. All right, so then looking kind of at a next question, this is kind of moving on to our next topics. So why is it more painful for me to touch the metal pot while boiling water in it as opposed to the ceramic mug with boiling water in it? So right now I'm touching this mug and it's not too bad. It's a little warm, but it's not like, ouch, I'm burning my hand, it's on fire. It's not like that hot. So what we can say with this is we're kind of thinking about this process of heat transfer, and we can say that different objects have different abilities to transfer heat. And we're going to look into the factors that cause that in a second. So heat transfers at different rates depending on the object, and the property that we're talking about really with the pot versus the ceramic mug is called thermal conductivity, but we're going to look at every aspect that causes this difference. So if we're looking at heat transfer, we said that this process of transferring heat has to happen between a hot object and a cooler object, so with some sort of temperature difference, one at a higher temperature than another. So I kind of have the red one, and then the blue one is going to be the colder one. So it's going to transfer overall from higher temperature to lower temperature. And we talked about how all these particles are on average moving with the same speed, but some may be faster, some may be slower. Back in the day, we looked at those distributions where we said, okay, like on average, this is kind of where we peak out, where a lot of the particles are, but some are going to be on this side of the curve, and some are going to be on that side of the curve. Some are going to be faster than average, some are going to be slower than average. So when we're looking at heat transfer, on average, we're going to say it's going to go from hot to cold, warmer to colder. So the net heat transfer is going to be from the warmer object to the colder transfer. That's the way that our energy, our heat, is going to transfer. But some of these particles in the colder object may be moving faster and may be giving some energy over here, but we're looking at this net flow. So overall, statistically looking at this, most of the hotter particles, the warmer particles, are going to be exchanging this thermal energy with our colder particles. So on average, we have this flow. And when we're looking at this heat transfer, this rate of heat transfer with these particles colliding with one another, there's different factors that are going to affect this. So if we're looking here, we kind of have the hot object. So we can picture the hot object as the water, the boiling tea. And then my hand is kind of the colder object. My hand is just at room temperature. So there's some barriers in between, and we were looking at the difference between the barrier, this green thing, either being the mug, I keep on pointing down here like you can see it, either being like the mug or the boiling pot. So if we look at this, the heat transfer is going to depend on different properties. Here we're looking at the property of thermal conductivity. So different materials are going to transfer heat at different rates, and that's just going to be based on the actual particles themselves. So maybe they move more freely, maybe they have the ability to flow more, maybe they have more mass, so they're harder to get at a higher kinetic energy. So there's lots of different factors that could affect the thermal conductivity, but it's really just a property of our objects. And what we can say with thermal conductivity, if we're looking at this, we can say lower thermal conductivity means less thermal conductivity and won't transfer heat as quickly. And one thing I just want to kind of go back to really quickly is when we're looking at heat transfer, one of the things that we really care about is the rate of heat transfer. So how much heat is being exchanged over some amount of time. So the rate is really important because eventually everything will kind of equal out, but it depends like, hey, how quickly is this happening? Like if I get all the heat of the water or heat of the tea, if I do it over a period of like a day, it won't hurt very badly. It won't be that exciting. But if I gain this heat in the matter of seconds, that would hurt pretty bad, and that would be bad. So we care about the heat flow rate. So we have this equation that's kind of guiding this. This Q is our heat term, and then we're putting it over some change in time, some rate. So we're taking heat per time, so we're turning it into a rate, and we're looking at the factors that affect that. So we said, okay, well, we have the thermal conductivity. This K is going to affect it. What we can also say is wider objects are going to transfer heat more quickly. So here we kind of shrunk down this object that's conducting our heat, and we can say that it will increase with the width of our object because there's going to be more opportunities for collision between these particles. So this area, this cross-sectional area, has an impact on the rate of heat transfer. So if I did have this full green thing, I have a lot of particles in that green object that can receive this energy that we can have these collisions with. I can have a collision here, 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 a collision here. I can collide all over the place. If I have a really small object, there's not a lot of opportunities for me to collide. Only a small little bit of area is able to collide with these cooler particles and transfer the energy to those cooler particles. But if I have more spaces, then I have a greater ability to transfer that heat to have these collisions. So the area, if we increase our area, will increase our ability to transfer heat. And then the next thing we're looking at is we're going to say heat transfers slower when there's less of a temperature difference. So if we have a lower temperature difference between these, if they're at about the same temperature, then heat won't transfer as quickly. So when we think about this, we can say each collision gives less energy and transfers can happen more often each way. No temperature difference, no net heat flow. So yeah, so if we have both these particles at kind of the same temperature, it won't energetically make a lot of sense for them to transfer this heat because they're like, hey, I'm at the temperature that you are. Whenever I have these collisions, we'll just have these nice elastic collisions where we'll bounce off each other and this energy will stay the same. Like we'll just kind of be like, oh, okay, I have this velocity, you have the same velocity. Great, now we're bouncing away with the same velocity. So yeah, the most extreme case we can think about with this is when our heat transfer ends. We said that heat transfer is going to end when we have no temperature difference. So when we have the same temperature on the hot side and the cool side, when they've come to this thermal equilibrium, then we'll no longer have any exchange of heat. So we have this delta T term equal to 0, then our Q over delta T term, this change in heat over time, will also equal 0. So then I thought I had one about the length. I totally had one about the length. But the last thing too is, okay, so I just threw this together really quick. But so we have that term L on the bottom of our equation that tells us that if the object is longer, if we have a greater thickness, if this green thing was a lot longer, a lot thicker, then we'll have a slower heat flow rate. Because if we think about it, if we put that red object and the blue object right on top of each other, all the particles in the red object will be able to collide with the particles in that blue object, and we'll be able to have this nice exchange. If we have a really long object in between them, then this energy is going to be kind of sucked up. It's going to be used transferring energy to this green object. So that will have to heat up, and then that'll come to equilibrium, and that'll be at some certain speed. And then we can start having the objects, or the particles in the green object colliding with the particles in the blue object, and then heat will transfer like this. But the longer that green object, that object in the middle is that's conducting, the longer that is, the more energy we have to give to that object, and we have to have these collisions so that all the red particles are speeding up the green particles, which are then speeding up the blue particles. So we have a really long object, it's going to take longer because we kind of have to get through that green object. So then we're talking about, how did the water in my pot get warm? So the water wasn't actually touching the fire, so explain on a particle level why that was happening. So when we look at heat transfer, we have a few different methods that we can transfer heat, and we really have three main ones that we're going to talk about. So one of these methods, and I really like this, I found this website, we don't have to really look at it, but it's just like nice little images that I stole the images and I just put them in here. But it's got nice images. Here's one, kind of based it all on, hey, you're at a camp out. Toasting a marshmallow, what's going on with that? So the first method that we're going to look at is conduction. So conduction is when heat is transferred when the object is actually touching. So the hot object is physically touching the cool object. And if you kind of look at this image, it looks a little bit weird, but that's kind of a stick that a person put a marshmallow on. So they're looking, okay, the one end of the stick is getting warm, the other end of the stick is kind of colder. So we have the warmer side of our stick physically touching the colder side of our stick. So when we're dealing with heat transfer from conduction, the particles are physically colliding with each other. We have these warmer particles coming in contact with these colder particles, and as you see in this image, the warmer ones are giving their kinetic energy to the colder objects, speeding them up. Then they can give their energy to the next row of objects, or particles, then to the next, to the next, to the next. So we really have a bunch of small-scale particle collisions happening. We're saying, hey, this particle is colliding with this one, which is colliding with that one, which is colliding with that one. It's kind of like one of those like Newton's cradles, where you swing the one ball up and then it collides with the other ones, except for it keeps on going, or it keeps on giving that kinetic energy. So we can think about kind of momentum transfer and a bunch of these small-scale collisions where an object will give kinetic energy through a collision. So here's a really nice visual with it, again, where we're saying, hey, we have this increase in kinetic energy, which is then giving kinetic energy to the next one, to the next row, to the next row, to the next row. So we really have this transfer of heat from this actual collision of the particles. The next one we're looking at, again, I think that they gave really good images, is convection. So this one, instead of the particles eventually kind of giving and passing through this energy, so it's kind of passing on the energy, with convection, the way that heat is transferred is that the particles themselves are physically moving. So we have these particles with a greater kinetic energy physically going to another object and giving them that heat. So heat is transferred when a fluid flows between a hot object and a cold object is kind of a definition for our convection. So here we see the particles down here, these air particles closer to the fire, they're heating up, they're getting warmer, they're gaining this heat, so where they're gaining the thermal energy from the fire, so we have this heat transfer between the fire and then the air, and then the warmer particles, they become less dense, they start to move up. So if we were up here, we would feel hot because these particles with more kinetic energy, with more thermal energy, are physically coming in contact with us. They're physically moving to us. So kind of our difference, I don't know if this is going to make sense, but kind of our difference with conduction and convection, I just thought about this on the fly. It's kind of like if you were across the room from somebody and you had to give somebody a letter. Conduction would be like if you lined up 20 people in a row and you said, hey, can you give this letter to somebody across the room? And they said, okay. And then you pass it to the next person, and they pass it to the next person, and they pass it to the next person. You kind of pass this letter across the room. That'd be like conduction. That would be like, oh, you're passing it from object to object. We have like this transfer between these objects themselves. Convection would be like if you took the letter and you just walked across the room and you gave it to that person. You said, here you go, here's your letter. I don't know why a letter popped to my mind. That's kind of I don't think I've written a letter in a long time. That's not true. Physical letters are wreck. I've written those. Yeah, so convection, we have these particles themselves are physically on the move to transfer this energy. And then the final one is the weirdest one, especially because we didn't get to study light, which we were gonna do, but then this happened. So with this, the last method is radiation. So you'll kind of have to take my word for it, but light is a form of energy. So when light is emitted, it can transfer that energy. So radiation is just heat transferred when light emitted from a hot object strikes a cooler object. So when we have this fire, when we have a fire going, it provides this infrared radiation, which is a form of light, which can be transferred and physically give energy. It can give energy to those particles, which is why when you go outside on a nice hot sunny day, back in the free times, you would get sunburn and you would say, oh, my skin got burned, because we have this energy from the sun is physically transporting this energy to you via radiation. So then if we're kind of looking at this process about how my pot actually got warm, my pot of water, and even though the water wasn't actually touching the fire, what we can say is, well, fire is radiating some heat to the bottom of the pot. And we also have a little bit of this heat transfer via convection, convection, and that there's air down by the fire. Those particles are getting warmer and they're physically moving to touch the bottom of the pot. So we kind of have this two-way where we have radiation and we also have convection that's heating the bottom of the pot. The bottom of the pot itself has some sort of thickness to it. So the bottom particles they got some heat, or they were heated. They got some of this thermal energy, and then this thermal energy was transferred through the bottom of the pot and then conducted to the water in the bottom. And then the water is going to both kind of conduct and convect heat until it gets up to the part of the water where the tea bag was in, or where I guess like the top of the water, whatever. But so the water particles are physically moving, And then we also have some conduction where the particles are running into each other until eventually that pot kind of comes to the same temperature. All right, so then quick little question, quick little thing to think about is just a quick little break to get our vocab in here, get our ideas in here. Let's say I put a metal spoon in the tea. Eventually the handle would feel warm. So I want to know why. So take a quick second, pause it, and then we'll talk about it. Yeah, so if we're thinking about heat transferring through a solid, this solid spoon, the particles themselves are not physically on the move. That would be weird. You'd probably be able to see that or feel it if every time something got hot, you would like see the particles from the bottom of the spoon work their way up the top of the spoon. That'd be weird in a solid. We'd say hot molecules produce thermal radiation, which cold molecules absorb. That's not quite true. We don't have this emission of radiation. I guess if you get it really, really hot, yes, you'd have some radiation, but we're not dealing with any temperatures that extreme. Looking at C, higher energy molecules hit lower energy molecules and on average tend to reduce the temperature between the difference between the ends. That one looks great. That's kind of our definition of conduction, where we're saying, hey, down here in the boiling water, the particles are moving real quick, so they're moving fast, and then they're like, oh, well, here's a slower particle, I'm going to hit that, and then they're both kind of moving kind of quick. And then this one says, oh, well, here's a slower moving particle, I'm going to hit that. And then that transfers up the spoon until on average they kind of have the same temperature throughout the spoon until we come to this thermal equilibrium where everything is going at the same speed. All right, so this was from the AP, their video about this. And I took a lot from their video. I'll link their video, but if you watch it, I took a lot from it just because I want to make sure I'm getting the things that they think are important. Because I feel like they may know more than I do. So I want to make sure that I'm teaching what they feel is important. So I took a lot from them. If you've been watching theirs or if you want to watch theirs, you're going to see the same questions. I just kind of added my own little T-spin on it because why not? You got to make it interesting, got to make it relatable. So kind of the main takeaways, heat is not temperature. Heat is the flow of thermal energy because of temperature differences. Temperature is related to kinetic energy. Temperature is therefore related to the square of the average velocity of the particles. And thermal energy can move by conduction, convection, or radiation. And then some questions that we want to be able to answer is there such a thing as cold? We can say no, it's just really this absence of heat. Why does a metallic object at room temperature feel colder than a room temperature wooden spoon? So think about that. Think about our equation for heat transfer. And then what happens to the motion particles as they reach absolute zero, where we have this zero temperature. So what would happen based on our equations for kinetic energy and temperature if we were at zero temperature? So that's what I have for today. That was a little bit long. Then I'll kind of run through some practice questions and you'll have the Google form. But this was just a brief little, hopefully brief, video lecture about what we have going on with the first part of thermo. Okay.